Today, we're diving into the exciting world of big data and how it fuels scalable machine learning applications. Our goal is to understand how we can unlock powerful insights from these massive and complex datasets. Let's begin by exploring the core pillars that define what we mean by big data in today's world. Understanding these essential characteristics is crucial for effectively working with big data challenges. First up, we have volume, referring to the sheer size of the data we're dealing with. This means immense quantities of data are constantly being generated, collected, and stored every single day. Next, let's consider velocity, which is all about the speed of data. It describes the rapid speed at which data is both generated and needs to be processed in real time. Then we have variety, highlighting the many different forms data can take. This includes diverse forms of data, ranging from highly structured tables to unstructured text and images. Finally, we discuss veracity, which addresses the trustworthiness of our data. Veracity emphasizes the importance of ensuring the quality and accuracy of the data we analyze. Now, let's compare two titans in big data processing, Hadoop versus Apache Spark. We'll explore their key differences to understand when to use each for your big data processing needs. First, let's look at the strengths that make Hadoop a powerful tool for certain tasks. Hadoop is truly ideal for large-scale batch processing, handling huge amounts of data efficiently. It's also very cost-effective, running well on readily available commodity hardware setups. Furthermore, Hadoop offers robust HDFS, its distributed file system, for reliable data storage. Now, let's shift our focus to the notable strengths of Apache Spark. Spark excels with faster in-memory computation, leading to significantly quicker data processing. It flexibly supports both traditional batch processing and crucial real-time data streams. Spark also includes mlib, a powerful built-in library, ideal for scalable machine learning tasks. However, Hadoop also has its limitations, which are important to understand. It can be slower compared to Spark, primarily due to its reliance on disk input-output operations. Working with Hadoop often involves more complex map-reduce coding, requiring specific programming skills. Crucially, Hadoop primarily lacks robust real-time processing capabilities, limiting its use cases. Similarly, Apache Spark, despite its power, also comes with certain limitations. One key limitation is its higher memory consumption, especially with very large datasets. While powerful, Spark can become complex for extremely large and intricate processing jobs. Finally, Spark often requires more powerful and thus more expensive hardware for optimal performance. Let's explore the different distributed computing architectures that enable machines to collaborate. We'll examine the various ways multiple machines can effectively work together on large datasets. First, consider shared memory, where multiple processors access a single common memory space. In this model, multiple processors efficiently share one unified memory space for quick data access. Next, we have the shared disk architecture, a different approach to data sharing. Here, multiple computers all access a common central disk, sharing the storage resource. Finally, let's look at shared nothing, a highly scalable and independent architecture. In this setup, each node operates independently, with its own dedicated memory and disk storage. Let's explore the Spark mlib workflow, which is a powerful framework for machine learning tasks. We will walk through the essential steps required to build scalable machine learning models effectively using Spark. First, we begin by loading our data and performing necessary preprocessing steps to prepare it for analysis. Next, we use this prepared data to train our chosen machine learning model, teaching it to recognize patterns. After training, it's crucial to evaluate our model's performance to understand how well it generalizes to new data. Then, we tune the model's hyperparameters, optimizing its settings to achieve even better and more accurate results. Finally, the refined model is deployed to make real-time predictions, applying what it has learned to new inputs. Now, let's understand why cloud platforms are so vital for handling big data challenges today. We'll discuss how leveraging the cloud provides scalable and efficient solutions for all your data needs. Let's start by looking at the key advantages that cloud platforms offer for big data applications. Cloud platforms provide scalable resources on demand, meaning you only use what you need when you need it. They significantly reduce the burden of infrastructure management, letting you focus on your data. You gain access to powerful machine learning services without needing to build them from scratch. Cloud models are cost-effective, offering pay-as-you-go pricing, so you only pay for what you consume. Beyond advantages, let's consider the core benefits that cloud platforms bring to big data projects. They enable much faster deployment of solutions, getting your big data projects up and running quickly. Cloud platforms offer global reach and robust disaster recovery options, ensuring your data is always safe. You also benefit from enhanced security features and compliance standards, protecting your valuable information. Ultimately, the cloud allows you to focus solely on your data and insights rather than managing hardware. Choosing the right cloud platform is a crucial decision for your big data and machine learning projects. It's all about matching the specific strengths of each platform to your project's unique requirements. To begin, consider your existing technology ecosystem and what tools you are already familiar with. For instance, if you heavily use existing Microsoft tools, your choice becomes much clearer. In that case, choosing Microsoft Azure would likely be the most seamless and integrated option for your needs. Alternatively, if you highly value Google's cutting-edge AI and analytics services, that points you in another direction. If that's the case, then Google Cloud Platform, or GCP, would be your ideal choice for those capabilities. And if neither of those specific criteria apply, always consider Amazon Web Services, or AWS, as a versatile option. Let's dive into a compelling case study: how Amazon leverages big data to enhance its customer experience. Amazon uses big data to provide highly personalized product recommendations, a key part of their business model. By analyzing vast amounts of customer behavior, like purchases and browsing, their algorithms predict what you'll buy next. This real-time processing significantly improves the shopping experience, boosting sales and customer satisfaction. Let's explore a practical application with a case study on predictive maintenance within the manufacturing industry. Here, big data and analytics predict equipment failures using EOT sensor data, enabling proactive maintenance and reducing costs significantly. Now, let's delve into the key advantages that make SparkMLib an indispensable tool for machine learning. We'll explore why Spark is absolutely crucial for building and deploying scalable machine learning solutions effectively. First, let's talk about scalability, a core strength of SparkMLib for handling vast amounts of data. It efficiently processes petabytes of data across distributed clusters, tackling even the most massive datasets with ease. Next, consider its incredible speed, which is a major differentiator for real-time applications. Spark uses in-memory computation, leading to significantly faster processing compared to traditional disk-based systems. Another advantage is its ease of use, making it accessible for a wide range of data scientists. Its high-level APIs in languages like Python and Scala greatly simplify development for data scientists. Then there's its seamless integration, allowing it to fit perfectly into existing data ecosystems. It seamlessly integrates with other Spark components, creating complete end-to-end data pipelines effortlessly. Finally, SparkMLib excels in distributed machine learning, a necessity for big data models. This feature enables the parallel training of complex machine learning models across many machines efficiently. To wrap things up, let's review the key takeaways and important points we've covered today. These are the essential points you should remember from our discussion on big data and ML. Remember, big data frameworks like Hadoop and Spark are essential for effectively processing truly massive datasets. Hadoop is great for batch processing, but Spark shines with faster, in-memory processing for real-time and ML. Distributed computing provides scalability, fault tolerance, and parallel processing, which are crucial for large datasets. Cloud platforms like AWS, GCP, and Azure offer scalable infrastructure, and managed services for big data and ML. Spark MLib is a powerful, scalable library for building advanced machine learning models on distributed data. Real-world case studies highlight big data's impact on recommendations, predictive maintenance, and fraud detection, among others.